Okay, hello everyone. So today, just a quick stream. We will try to have a look at the components that we maybe must swap on the board, do some calculations for the power supply. We will need to design some filters, and maybe try to also find a few shields that we can add over the different subparts of the system. And finally, if we have some time to do that, try to continue doing the small improvements to the board. So let's fire up KiCad. So last time I discovered that the two inductors that I use for the power supply, so that is that one and that one. So the components are now not recommended for new design, and so I would like to change them. So I had a quick look previously, and it seems that they do have components from the same manufacturer, the same value, the same footprint. Some characteristics are just a tiny bit different, so I'm gonna have a look at the reference for them, update the reference in the schematic, and finally do the new calculations with the new values for the filters of the system. But there is a twist, because the datasheet doesn't specify. I think there is something lacking in the datasheet with the fact that they do not explain how to compute a specific component, and so we will have to do some research and find where we can find the value and the equations for that, do the calculation, and place it on the board. I think we may have to add also two components, but I think it will be easy enough to do. It shouldn't influence too much the current design. Okay, so let's get started. I will go on DigiKey, which I configured in English for you today, and we'll go in the passive components, inductors, fixed inductors. So the 1.8 volts, so we'll go have a look at the schematic rather than the PCB. And so, okay, we'll start then with the 3.3 volt rail, which is that one, and it is 33 microhenries. So we will go here and go to 33 microhenries, which is a standard value, so we will have plenty of them. We want them to be in stock. Also, we want them to be active, not to do the same mistake as previously, and we want them shielded. Okay, so we already narrowed it down to 472 components. Current rating, I'm gonna have a look. I think it was, yeah, in this document. So that's a document I wrote when I first designed the power supply, and I had that for the 3.3 volt rail, which is the first buck, inductor choice, the value is here, and this is the ripple current and so on, but what we are interested in is the current, the peak current, which is 575 milliamp. Also, we want to take care that maybe if we add other devices later on, this current might increase. So I will try to pick higher than just 575. So the current rating, I'll pick at least 800 milliamps. And we can go maybe not to, I think 3 amps is quite a lot already. And it's the maximum that the buck can output, by the way. And same way here, saturation. So current rating, it's the maximum current that can go through without the coil overheating or something like that. Saturation, it's tied to the materials from which the core of the inductor is made, and at some point, if you have too much current going through the inductor, the magnetic field in the core will be so high that the core is really saturating, and then it behaves as if it was air in the coil instead of ferrite or iron or something like that. And then you reduce your inductance by quite a lot. So we want that to be higher than the current that we expect. So let's pick about 802, and then we can go as high as, yeah, the maximum that they have here. Okay, we will sort them by price, because I think that, yeah, the one that I want, I think it's that one. Oh, they have that one too. So we see that it's Uden for the manufacturer, which is the same as the one that we have currently. What I want to have a look at is the footprint. The footprint, you see that this one is 6 millimeters by 6 millimeters, and that one is 4.9 by 4.9. This is the footprint that we already have on the board. So, hi Andy, welcome. So I think you're the first one here, so don't hesitate to tell me if something goes wrong. So I'm trying to have a look at the components to replace the inductors on the board, which are not recommended for new design. So I'm looking at the 3.3 volt one. This is the reference of the older one, and this is the reference of the new one. So we can see that it's the same actually. I'm gonna copy the reference to show you. Yeah, like that. Okay, so it's this one. And we see that it's 4.9 by 4.9. It's a square. So if we have a look at that one, we can see that it's basically the same form factor. It's the same height too. Maybe I'm gonna have a look at the datasheet to be sure of that. Ah, they don't have the datasheet on that one. Well, we are gonna have to have a look at the manufacturer's website. Okay, spec sheet, characteristic data. Yeah, okay. Okay, so this is the footprint that they recommend. And that one, that's the footprint that they recommend. So, yeah, 1.5 by 4. And if we look at A, we were looking at NRS 5030. NRS 5030, where is it? Yeah, okay, NRS 5030. A, it's 1.5, same here. Spacing B 3.6, same, and C is 4, same. Exactly the same footprint. So I'm gonna pick that. So then it's easy. We go on DigiKey, we copy that, we go to the schematic, and we modify the value. Done. We are gonna do the same for the 1.8 volt coil. So go here, and it's 47 microhenries. So just gonna remove current rating, current saturation, and inductance. And so inductance, I'm gonna pick now 47 right here, which is also a standard value, so we are gonna have plenty of choice. I'm directly gonna pick the same manufacturer, I think. I want to avoid having to change the footprints. So yeah, here, and then we go on the right of the screen. Have a look at the sizes. Ah, okay. So they, it's annoying. They do not have one, which is the same. It seems quite annoying. And they all are rated for quite, yeah, not much less current, but we won't have that much current going through. So if we go at this document, we see that the peak is about 300 milliamps. So we will be good with whatever is a bit higher than that. The 1.8 volt is probably not going to be loaded more than it is. 3.3 might be, depending on what we add on the board. So yeah, I'm gonna copy the reference and look at its characteristics. But I think I may have to design a new footprint for that one. We will see how it goes. No, I'm gonna pick the cheeky. Okay. So it's an RS5032. Yeah, it was the same series as the previous one, so same footprint and so on. Yeah, I'm just surprised that they don't have an inductor with the same footprint. This one is much larger, and all those ones are smaller. So this is the one that we picked for the 3.3 volt rail, and it's an LSXND 5050 LSXND. Yeah, okay, so they do not have one. Maybe LSXND 5050 XKT 470, and oh, what? Surprising. Okay, what do they say for naming? Do they have a specific convention? Yeah, it doesn't seem so. Okay, well, let's see the current rating, and no, let's order by DC resistance, increasing order. Oh, this is quite a lot actually. How much was the previous one? $325 milliohms. Oh wow. It's quite high. I'm surprised. Okay, then we will, so we said that we were having 288 milliamps peak. Let's pick at least 500. and sort by price maybe. Also, we want it to be not too high. Can we have this criteria somewhere? Yeah, it should be less than 3 millimeters, otherwise we are gonna have troubles with the shield, I guess. And we will have a look at size of it. So it should be less than 5 by 5. Maybe we can directly go. Okay. Okay. Which one is the most interesting? I like the first two. First one is a bit less expensive. Okay, which one should we pick? So the two here are above 10 megahertz, which is great, which is far beyond the switching frequency of our design, which is 400 kilohertz, and we should pay attention to that. So yeah, 400 kilohertz is quite low, so we shouldn't have any problem. Just in case, we should be careful. Third one, which size is it? 4 by 4. Yeah. Hey, Wojciech. Yeah, you're welcome. My pleasure. So yeah, I think I'm gonna pick the first one. So this one, which is 1/10 of a millimeter shorter in each dimension than the previous one, and it's 3 millimeters, so it's same as the other one. So it's not a problem for the shield. Okay, let's have a look at the datasheet. Maybe I'm gonna already paste the number right here. Okay, what does the datasheet say about it? Okay, they give a reference footprint, great. So let's fire up the footprint designer. So how are we gonna name that footprint? I'm looking for something that could tell us the name of the footprint. They don't seem to have it anywhere. Maybe I'm also gonna have a look at the standard library from KiCad, see maybe if they have one. So it would be in inductor, oh, SMD worth. Oh, okay, they do it like this. Would it be that one? So I'm gonna, yeah, WELQFS. No, they don't have it. Then I'm gonna name it just like the one that they give, except that what is the 4024? Is it the size? No, it can't be. Oh, size here, 4828. Oh. Oh, I guess it's the length of a side and the height of the device. Do they have 3D model for that one? I wonder. Oh, they do. Impressive. Anyway, okay, so I'm gonna copy the name. New footprint. The name will be LQSF, I guess, is it? LQSF 4828. Okay, so each pad is 3.6 by 2. I put that on the other screen. So size X, it's 3.6. Over. So it's 2 then and 3.6. And the spacing between the side of the pad and the center of the footprint is 0.7, so it should be at minus 1.7 millimeter and plus 1.7. Come on. Freeze. Okay. Okay. Case size is 4.8 by 4.8. So let's see how they did it in this one. Okay, so this is drawn on FFab layer. I guess it's the size of the device. Yeah, they do a chamfered corner. You can try to do that. So FFab and then 4.8. Like this. Okay. Okay, so this is centered. And then it seems that they have silk screen just outside of the boundaries. And then this is the bounding box, the area around which we shouldn't place any component. So okay, let's take the front silk screen and then draw something like this. What size do they? Trying to stay as close as possible from the reference design, let's say 0.12 line width. Well, let's increase it by 20%, like so. Okay, and also, yeah, save. Okay, they do it like that. So it would be for us from here to here. Okay. And then the bounding box, I think it's half a millimeter from the device. So if I pick a grid, oh no, it's less than that, no? Point 0.3, oh. 0.4. Yeah, I'm not gonna follow them on that one. I like my boxes to be square, especially if, yeah, the courtyard, as they call it. So let's do a square, especially if the device is square, it makes more sense. Yeah, like this. Oh. Okay, gonna do it larger than that then, because there we have the pads. Then okay, square. Let's go from here to here. So it's 5.4, and then let's add an additional 0.8 millimeters, so 6.2, and then make it square. Like so. And then center it. Okay, perfect. Great. So I think this is it. The reference maybe. And oh yeah, I'm also okay, but they have that on the FFab, and oh no, it's not the same component. They have the reference on the FFab and the name of the device also on the FFab layer. Yeah, okay, that one, so we put that here and that here. Also, footprint properties. If we have a look right here, we can see that, especially in the name, I'm gonna follow them on that one. Keyword SMT inductor description. Okay, so it's a shielded power inductor. Or maybe, what does the datasheet say about it? Does it say something? Okay, well, they don't. Body 4.8 by 4.8 by 3 millimeters. Files. Specifications. Do we have somewhere the specifications of the footprint? Oh yeah, dimensions right here. Okay, yeah, so this is the link that I want. Great. Okay. Okay, that's it for this one. So we can close that, and on the schematic, edit this, the footprint. It's in M17 MISC passives, that one. Okay, apply. Okay, that's done, that's finished. So we don't have any step file. I think they offer one for download on their website, but yeah, it's not open source as always, I guess. So yeah, remains a property of Ruth Electronic, blah blah blah. Yeah, so I don't think that we can put it in the GitHub. I think I sent them an email a while ago and they haven't answered, so maybe they don't care that much. Anyway. Okay, so then we should update the PCB. Okay, this footprint have been modified. Well, we can basically leave it as is. Yeah, just like that. Oh, what a fancy way to do thermal connection. Oh, can I maybe increase a bit the size of these? I would like to be able to have a connection all around the pad. Okay, but then I guess it's gonna break the sliver that I have just below. Not great. Maybe I can... Yeah, no, I shouldn't. Okay, well, not a problem. Okay, I think it should be great, just like this. Okay, so new inductor is in place. Now what's left is maybe yeah, no, okay, the vias are, yeah, it's not a problem. Okay, now what is left to do is open the datasheet from the DC converter and decide the new components for the loop compensation filter, as they call it. Also update the values of the components in this. So we have that one. So 1.8 volts. This is this one. Max current, it's 970 milliamps. And the saturation current is given right here. It is 560 milliamps. Series resistance is 260 milliohms. Okay, let's do the same for the new one for the 3.3 rail, which is this long name. Oh yeah, it's that one. So we have, no, not this document, sorry, this one. Reference, that's max current 800 milliamps, saturation current is 1.15 amps, series resistance is 225, typical. Okay, so now we go in the datasheet and I think it is yeah, okay, right here. So we are gonna have a look at everywhere where they use the series resistance of the coil. Where is it? Do they use it somewhere? Maybe they don't. Okay, well, anyway, we still have to compute the loop compensation. However, we are gonna have a closer look, because you will see that there is a problem somewhere. So first, they give the load resistance, so as if the load was a simple resistance, which in this case is not that much of a problem, because we consider kind of small signal circuit, which means that we consider small changes around the fixed value. So we can consider that the load can be approximated as a resistance, which will change, by the way. However, you see that there is the C1 right here, and nowhere do they give a value to compute, an equation to compute this value. This value is called the feed-forward capacitor, and these three components, so comp, it's a pin on the device, and it's the compensation loop, the loop compensation filter, sorry. So you see that this is the output, this is basically the system inside the chip, which decides if there is an error on the output voltage with respect to what it should be. So the output voltage is here. It's divided by R1 and R2, so that the feedback voltage is always at 0.6 volt. If there is an error, it's computed by this amplifier, and then it's amplified and converted to whatever the device needs to do with it here. And it means that if there is an error on the output, it is gonna compensate for this error. However, we do not want to compensate for every and each error on the output. If we have an error which is too high frequency, we won't be able to compensate for it. So we should not compensate it. If we compensate too fast or too slowly, then we are not going to have satisfactory results. Also, we could have a system which resonates at some frequency, which is hard to decide in advance. And if the system is resonating at a specific frequency, that frequency is gonna be appearing on the output voltage. And it can be quite a large ripple, sometimes a few tenths of a volt, which can be too much depending on the system that you use. So in our case, the FPGA is quite strict in terms of what voltage we should feed it. And if we supply too much or too little, it will increase the current consumption significantly or cause some malfunctions in the device. We should be careful with that. So this is the filter that is gonna avoid having any resonance and make it so that, to speak more in simple terms, to make it so that the device corrects the error at the correct speed, let's say. So these three components, you can see that we can compute it with equation 22 RC, 23 CC, and 24 CB. And CB is optional, but we are going to use it. What they don't give is the C1. Why am I speaking so much about the C1? Well, because if you look further than the datasheet, usually when you have ceramic capacitors at the output, which is what we have. So ceramic capacitors, it's basically SMD devices. So those are, in this case, ceramic capacitors. You have other type of SMD capacitors. It's not the only one, but I know that these are ceramic ones. Ceramic capacitors are nice because they don't get old like the electrolytic capacitors, which can dry and then the value of the capacitance is gonna change and so on. So that's that's one of the reasons that we like ceramic capacitors. One of the other characteristics of them is that they have very, very low series resistance. So that one, so the RESR here is not a real component on the board. It's what is in series with your capacitor C0 at the output or CO at the output. It is present in the electrolytic capacitors. It can be a few ohms or a fraction of ohms depending on the brand, the value, the size, lots of factors. In our case, it's much less than an ohm. It's sometimes in the milliohms range. It's very low. And this can cause some problems and some resonance at the output too. That's why usually if you have this kind of filter, you add a C1 next to the R1 of the feedback divider so that you can compensate for a ringing which is going to appear at the output. So I hope that I'm not losing you in my explanations. If you have any question, don't hesitate to ask in the chat. I'm gonna re-explain whatever I need to re-explain. So that's why I've been talking about this filter for in the next few episodes, that I need to redesign it, and it can be quite mathematical. I'm not gonna go into the math because I think I have a fix for this issue. I just wanted to explain why it is an issue, why I'm gonna go, why I'm gonna do what I do right now. So we are in a specific case not described in the datasheet where we need to add a component for which we don't have the equation in this specific datasheet. I already told them about that using this specific link. It was just a few days ago, so they haven't answered yet, and I don't think they are gonna answer anytime soon. Can take, I would say, at least a few months. Anyway, so if you look at the datasheet, you see that they explain how to compute the value of the inductor, what is the current that's gonna flow in the inductor, so that you can know which specific reference to choose. They give the characteristics of their example design. If we have a look at this typical application, you see that they have feedback, yeah, this one. So they have 20K and 20K, so this is going to be a 1.2 volt, yes, because the feedback is 0.6 right here. And they have this C26, which is the C1 from previously. If we have a look here, same thing. And if you have a look at FB3, where is it? Yeah, here, same thing. So 22, 22, 22. They have 22 everywhere, and I don't know why. Nowhere do they explain what to choose for that. So yeah, going just quickly through the datasheet to see if I haven't missed something. I don't know, maybe I have, but I've gone through it a few times already, and yeah, I didn't read anything about that. So this is for the under voltage lockout. Power failure detection. Output voltage right here. So this is where you design the divider bridge. They give that, and they don't speak about a capacitor. You can also see that in the functional block diagram, they do not add it. So it's a bit of a mystery when you look at the datasheet. Okay, so then how to fix the problem? Well, we'll have a look, and I'm just gonna pick a device which is very similar to it, which I first tried to use for this design, but I picked this one after that because it has a lower, the one we use does have a lower quiescent current, which is the current that the devices use when they are turned off. So basically battery drain when the device in the radio is in your drawer. Okay, the datasheet is kind of the same, basically, just different values, different names, different graphics, blah blah blah. Output voltage, you can see that also here that they give you the equation for the resistor, but they don't speak about the capacitor, except of course for the output and input capacitors, which are different from what we are talking about. Typical application. Okay, so now you can see that they added it. You can see that here it's 4.9, 4.7, sorry, 4.7, and FB2, where is it? FB2, yeah, here. This is FB1 and FB3, yeah, 4.72. Okay, C feed forward. Yes, okay, so that's the equation that we want. Let's compare the two sections between the data sheets to see if the equations are the same. So for RC, 2 pi times FC times VO times CO divided by GM times VREF times GM. Exactly the same. Perfect. And then we have a look at CC. It's RL times CO divided by RC. Great. And then CB, which is C roll in this case. And it's RESR times CO divided by RC. So great, same thing. And then yeah, so we have CFF, which is the one that we are looking for, which is 1 divided by 2 times pi times f of the 0 of the of 0 FF, Z is for 0, we are gonna have a look at that, and then times R1, which I don't know what it is. Oh yeah, it's the divider bridge resistor. Okay, so what is this FZFF? Let's read. So calculate C. FF stands for feed forward. Calculate C feed forward compensation 0 at low frequency to boost the phase margin at the crossover frequency. Make sure that the 0 frequency, FZFF, is smaller than soft start equivalent frequency, 1 over TSS. Okay. So we are gonna add a 0 and it must be smaller than soft start equivalent frequency. Okay. Maybe I can try to do a quick drawing to explain some. Sorry, it will be some theory about control systems, because this can be quite interesting in my opinion, even though it's not my forte. So we are gonna draw a graph that we call a body plot. So maybe we can use that. Oh. Okay, and so on the x-axis is the frequency, and on here it's the gain, basically how much does the device or the system try to fix an error which happens at that frequency. So if we have an error at a low frequency, basically it's the error at the output that you read with your multimeter. If you see that you ask for 3.3 and you are at 3, then there is 0.3 volt error at low frequency. So we want that correction to be as large as possible. So we want the frequency to be precise. And then for some reasons, which we are not gonna go into, the correction is gonna be lower for some at some points. It's gonna go smaller and smaller and smaller and smaller and smaller. This is not gonna be a straight line, but we can say that it's gonna be, because yeah, we don't care really. Also, with another color, I'm gonna draw the phase of the response of the system. What does it mean? It means that it's basically the sign of the correction, or is the correction in phase with the error. So if I have an error at 10 Hertz and I correct it exactly. Oh yeah, my camera is maybe in the way. Can I? Like that. Okay, so if I fix the error exactly as it happens, then I'm good. If I fix the error, it's oscillating, and if I'm too late and I add the error when it's too high instead of too low, because it's oscillating, so it will be too high, too low, too high, too low. If I add the correction when it's too high instead of too low, and subtract when it's too low instead of too high, then you can see that it's gonna be amplified. and then this error is larger, and so we try to fix it again, but it's again in the opposite way. So it's just gonna amplify and amplify and amplify, and then we are soon gonna have an explosion. Yeah, the chat is in the way, but the chat is not it's a bit transparent, so I think we should be good. So the phase is basically, are we fixing it at the right time? So this is gonna be 0, we call the phase in degrees, and then this is gonna be 180. If we fix it at 180, that we are perfectly out of phase, so we are basically adding the error to the fix to the error. So we are amplifying the error. So then, what are the specific points of interest in this graph? Well, the gain here is gonna be high, let's say about 60. And we usually use dB for the units. There is some points at 0 dB where the correction is equal to exactly 1. And then below 0 dB, then you are gonna try to fix the error, but your fix is not enough. So you don't compensate enough for the error, so the error is gonna basically stay there. And yeah, it's sometimes you cannot fix the error because it's out of range. So if the switching frequency is 400 kilohertz, you will not be able to fix an error which is at higher than 400 kilohertz. So what do we want? Basically, at 0 decibel of gain, we want the phase to be less than 180. So this system is here, as it is designed, is not realistic. It's very, very good. So 180 degree phase. Oh, sorry. Okay. What's happening? Okay. Okay. So basically, right here. Oh no, I'm gonna choose red. So we have this, and it is called the phase margin because it is how close we are from 180 degrees at the 0 decibel point. And then also at the minus 180 degrees, right here, we want to know how close we are from the 0 dB line. And it's called the gain margin. So basically, at minus 180, at 180 degrees, you do not want to amplify the error. Otherwise, it's gonna explode. And at the point where you just don't amplify the error, you don't want the margin to be 180 degrees. And those are the two main criterion that you are gonna look at when you design the compensation filter, or basically a filter for a linear control system that we call. Okay, so let's have a look at the data sheets again. Okay, so the phase margin at the crossover frequency, it's this value. We want it to be high, usually about 45 degrees, I think. And so this is gonna help with that. So I'm Gonna have a look here. Okay. So I picked a value for the slow start. Soft start, yeah, it's 1 millisecond. And so then it's 1 kilohertz for the F, for the 1 over TS. But first, oh yeah, no, I don't need to reevaluate the equations, I think, but except that maybe I'm gonna do it because I'm not sure that I computed it correctly. Okay, so I'm just gonna go through to see if I'm doing things correctly. I don't want to be doing that too many times, so it's gonna be a bit quiet. So what I'm interested in is trying to see what they recommend for the RL. But I think it's gonna be the equivalent resistance of our system at the designed load. So in my case, I designed it for back 1 output current 500 milliamps. Just gonna Python is here. So we have 290 for MCU plus 80 for the transceiver, and the speaker is about 0.7 watt, I think. Yeah, okay, maybe 500 milliamps is... Yeah, okay, it's not gonna change that much for what we do here. Anyway, okay. So we are just gonna recalculate the recommended values here. Or maybe we are just gonna use these equations. So this one is a bit different. They don't have the V output divided by Vref. Let's see what we get. So we have 6.18 times FC, crossover frequency. Yeah, I'm gonna use what they suggest, so 40 kilohertz times C output, and C output it is 3 times 4.7 microfarad, I think. Quick look, yeah, that one, 3 times 4.7. And then divided by GM times GM, and then we are gonna have to go in this datasheet to have a look again at what our GM are. So there is one which is, so parenthesis 300 microsieverts, and then 7.4 amps per volt. We have 1600 ohms basically. Okay, so this is gonna change a lot actually. What if we had like 3.3? Oh yeah, times 0.6. Yeah, of course it's gonna change. Okay, no worries. So this is now RC is that. I'll have a look at DigiKey to see what kind of values are standard values for the resistors. I'm looking at it on the second monitor, so you won't be able to see it, but not a big deal, I think. Okay, so 0402, we want that to be 1% or lower tolerance. To be in stock, blah blah blah. Okay, resistance. So yeah, I can't find one which is particularly okay, it seems that 1.6 is common enough. So no, sorry, I'm gonna close that. This one is now 1.6 kilo ohms. Then we keep going on the data sheet, and we see that this is RL. So RL, we are gonna have about 500 milliamps. Yeah, so it's equivalent to about 6.6 ohms. So we have 6.6 times 3 times 4.7 micro. All this divided by RC. And here it gives a CC of 58 nanofarads, which we are gonna round passive components, capacitor, ceramic capacitors. Okay, so we want to be about 58 nanofarad. We want that to be in stock. We want that to be 0402 Ks. And also we want that to be rated for enough forwards. Okay, let's apply that already. And I want that to be X5R or X7R for the dielectric value. Okay, so now we can have a look at the values that they have on the website. I think it's gonna be 47 nanofarads. It's not that close, but I don't think they have closer than that. Or maybe 68. What do they say? So it should be at least twice the crossover frequency. So that means that if we have a C which is too high, we are gonna reduce this value. So we should, if we have to choose, we should pick a C which is too low or lower than the one that we have to pick. So yeah, 47 nanofarad is gonna be good. Then C, oh no, it's this one, before, so we have to place it before. So if we want to place a 0 before, then that means that we have to pick a C which is higher, because the, okay, that's theoretical stuff, but the 0 created by a capacitor, which is a term, a mathematical term used when you do system analysis, it's 1 over C times S. And S is it's like the X in your equation. So that means that if we want to have a 0 which is before another one, so a bit lower, then maybe we can just pick a C which is higher, and then it would not be 47 nanofarad, it would be 68 nanofarad. Great. And then CB, which is this one, C roll. So RESR. The ESR is gonna be the ESR of the output capacitor, which is well, typically very low. It's so low that they don't give a specific value in the data sheets usually. So I'm not sure of what I should use. What should I... Okay, let's have a look at what Murata says. Okay, Murata says basically about 10 micro, sorry, 10 milliohms. I think it's gonna be in that range for the good brand. It seems that the higher the capacitor value, the lower it's gonna be. So I think if we pick 10, then we are good. Except that we are not gonna use 10, we are gonna pick 10 but not use 10, because we have 3 of them. So that means that the resistors are in parallel. So we have 3.3 milliohms actually of equivalent ESR. So yeah, we have the text that I added here, which is less than 1 ohm ESR. Because we have an ESR of maximum 0.3 ohms at the output given the design constraints, we are gonna be lower than that anyway. So 3.3 milliohms, what does the datasheet gives for the C if we have 3.3 milliohms? I guess it's gonna be a ridiculously low value. So it is 3.3 milliohms, so like that, times C output. C output is 3 times 4.7 micro. Then divide that by RC, which is 1.6 kilo. Okay, yeah, it's 29 picofarad. Very, very low. Let's see what they have on their circuit. picofarad. Yeah, okay, it's kind of in the range. We have a very low ESR, so it's, yeah, we can, I think we are good with that. So here we are at the CB of 29 for our ESR of 3.3 milliohms. And then we are gonna round that to we don't have a lot of choice here. Or maybe, oh yeah, maybe we can increase our choices if we allow for NPO or C0G capacitors, which are much better than that. So yeah, we can see that we have much lower capacitor value. And then, oh yeah, 27. I think 27 picofarad is gonna be what we need. Great. Okay, perfect. It's done for the 3.3 volts rail. No, it's not done. Sorry. We need to move that here. Okay, so sorry, what did I say? Right here, I need to compute the last value, which is the one that I did all this fuss for. It's CFF. Okay. So okay. Yeah. 1 over TSS. That is 1000. So we want FZFF to be lower than 1000. So let's see if we do 1 over 2 pi times 1000 times R1, and R1, what is its value? R1, it's 9530 ohms. 16 nanofarad, except that we want it to be lower than 1000. So, sorry, let me have a look at the equations again. So if we want it to be lower than 5000, we need to increase CFF. I think I will pick a value which is at least twice that. Why? First, because the value of the capacitor, it's not as precise as for a resistor. Usually it's not uncommon to have let's bring some lights. It's not uncommon to have 20% of error on the capacitor value. Also, the value of the capacitor, the effective value, it's gonna be lower also depending on the voltage applied to it, and I don't know what is gonna be this voltage actually. Maybe oh yeah, I tried a few things with PSpice the other day, and I don't know if I think they, oh yeah, I'm silly. We know that value, of course. It's the one around R1. So this is 0.6, this is 3.3, so this is gonna be 2.9. So we have 2.9 volts around the capacitor, and this is gonna reduce a bit the equivalent capacitance of the capacitor. So that brings me to the value that I must pick, which yeah, we have so 16 nanofarads, which I'm gonna try to double. And if we have a look at DigiKey for the common values, this here, so I'm hesitating between 33 and 47. Yeah, I'm gonna pick 47 nanofarad. And so now I must edit the schematic. And yeah, oh, okay. Let's move that like this. Move this. Like that. And now we can add the capacitor. We will add one here and one here, like that. and we decided to pick 47 nanofarad. If I have a look at their reference design, what did they use? They use very, very low value. I'm about 1,000 times higher than what they use, which worries me a bit. And in that one, so CFF. I don't really know what to do. So what do they use for slow starts? Slow start. Where is it? Soft start. Okay. Okay, it's around 1 millisecond for 4.7 nanofarad. And here, yeah, so they have a 1 millisecond soft start time. So they have the same design as I have. And here it's oh, they have 4.7 nanofarad. Oh yeah, but they have 40K, which is quite high. We don't have that much. Okay, I'm a bit lost. Thanks, Andy. But I'm lost nonetheless. Okay, let's have a quick look. I did this research previously, and TI does have a white paper or something like that. Yeah, it's not the exact value that we use. Okay, if we use this equation, what value do we have? It's not the exact same family, but it's not problem. 1 divided by 6.28 times 40k multiplied by square root of 1 divided by R1, which is 9,530, times 1 divided by R1 plus 1 divided by R2, and R2 it's 43k. And of course, so I have 460 picofarad. Does the datasheet mention anything about an equivalent CFF in the electrical specifications? So they have a switching resistance. They don't seem to mention anything. It will, however, it will have a specific value because of the maybe the internal value, but I don't know. Maybe they have also technical documentation. Do they give something? CFF here? Okay, so interesting application node. They describe a lot of things, but not what I am looking for. Yeah, okay. Evaluation module. They use 22 picofarad. Or 82 here. 82, 22, 22. Okay. I kind of like this value. Did I do an error computing the previous value? I think I did. Oh no, wait. Okay, okay. I think I'm gonna pick this value, 460, about that. So what do they have here? About 460 picofarad. (470 picofarad). Okay, so let's just take the link of the document, this one. Round to 470 picofarad. And so right here, okay, let's do the computation of the feedback loop for 1.8 volt rail, and then I think it's gonna be it for today. It's getting quite late, and I would like to eat at some point. Yeah, my very beautiful plot. Okay. Loop compensation. Okay. Compute again the values for RC. So 2 pi times FC times 2 times 4.7 microfarad divided by then times 300 micro times 7.4, and then RC is 1063 ohms. I think 1K is gonna be the closest value. Yeah, okay, 1 kilo ohms is good enough. CC, which value? So we designed it for 250 milliamp. So it is oh yeah, that's better. So then 7.2 times 2 times 4.7 e to the minus 6 divided by RC, which is 1000. Then we have 67 nanofarad. Closest value is 63, I think. What did I forgot. DigiKey, help me. Oh yeah, 68. CB or C-roll. So we are gonna use 5 milliohms because it's 10 divided by 2 because we have two output capacitors for that one. Divided by times 2 times 4.7 to minus 6 divided by 1000, so 47 picofarad. And it's a good value, so we don't need to round that. It's a very standard one. And finally CFF, then we are gonna have a look at the document we found, which called for 1 divided by 6.28 times 40,000 times square root of 1 divided by R1, and R1 in this case is 10,000 multiplied by that plus 1 divided by 20,000, and we find 487 . Picofarads, and we are going to use the same, so 470, yeah. Okay, so KiCad . Okay, let's plot the PDF file. Great. Can we very quickly import it to the board? Ah, yeah, no footprint, of course. So it can go right there, and this one can go right here. We need to move this via. Connect it like this. Same here. Okay, well, that's gonna be it for today, definitely. So yeah, quite excited to see that my microphone behaved today. It's great, I like that. Hi Bastien, so we are popping at the end of the stream because I'm gonna leave it here for today. So basically, we updated the values for the output inductors of the buck converters, and we redesigned the loop compensation filters. So yeah, I think I hope we did what we need, and we are gonna have a stable system. I can't guarantee that before having it in my hands and testing it. So the most important thing is that we have all the footprints at the correct location. So this one here and this one here, that's the one that we were lacking, and that I had to add today. We still can update the value of the components later on if we want. That's not a big deal, it's easy to do. But we can't add footprints later on. Oh, decompiling an STM32 memory. Well, good luck, and I hope you like Ghidra, because you are gonna need it. Okay, so that's it for today. Thank you everyone for following along. I hope I did not bore you too much with the math and the theory behind the control systems. It's a very complex field, and some people have a job where they only do that, design control systems. It's very, very complex, and yeah, I guess you can have lots of fun maybe doing that if that's what you like. That's not really my weed. Anyway, thank you everyone. 73s to all of you who are still looking, watching this stream, and I'm gonna see you in the next stream, where we are definitely gonna pick the shields for the 3 main chips, and maybe do also the, as I say every stream now, finishing touches or the small improvements. So that means the vias, maybe the battery connector and so on. I would really like to have finished this board in not too long, because we will need then to assemble it, to manufacture it, assemble it and so on, and this can take some time. And if we want to have the time to debug it and bring it to Friedrichshafen, then we really need to, yeah, we can't afford to lose time, let's say. Okay, so bye bye everyone, and see you next time.